All right, in our last primary video for the lessons, or for this section in the textbook at least, 3.4, independence, bases, and dimension. The last lesson left off with the statement that if you have two bases for a subspace, that the two bases have to have the same number of vectors. That the bases don't have to be unique, but the number of vectors in each basis for some space, if they describe the same space, must be the same number of vectors. And the terminology we use for that when we're counting the number of vectors in the space is known as dimension. And so when we talk about the dimension of a space, whether that's a subspace, a vector space, a subspace of a vector space, etc., we're essentially looking and trying to count what are the number of vectors that form the basis of that space. And in this video, it's hopefully a little bit shorter than normal in that kind of prove the idea. Now the statement was made and a couple of examples were shown in the previous one at the very, very end. But in this video, it's all about now proving this idea. And so I've written out, it's essentially the statement if the vectors v1, v2 all the way to vm, and w1, w2 all the way to wn are both bases for the same vector space, so they're describing the same space, then the big idea is that m has to be equal to n. That whatever number of these vectors I have, whatever number of these vectors I have, if they're describing the same vector space, then these must be the same number of vectors. They must have the same dimension. Now, in the proof, which is what I would like to look at, because the proof and the construction, any chance that we get to look at higher advanced mathematics, we should. Is to essentially almost perform a proof by contradiction. So we make an assumption, and as we walk through based off of this assumption, if we come across something that then can't be true, it means our assumption must have been false. And so notice in terms of the proof, we start with, well, let's assume that these two bases are bases for the same vector space, but that m isn't equal to n, that n is greater than m. In other words, there are more vectors in this space than there are, more vectors in this basis more than this basis. Now, because, and just kind of walking through the proof kind of in my own words, it just hopefully helps instead of reading the text. The idea is that because they're describing the same vector space, remember that every vector in the space, there's always a unique combination of basis vectors that project to that point. And so what we end up doing is we say, okay, well, let's go one vector in W at a time. And we say, okay, well, this vector W must be some kind of combination of these. And so we use V as the basis to form essentially this basis, because there are more vectors here in terms of calculating. And so what we do is we say, okay, well, let's assume that W1 is created by some linear combination, and we use A to represent the scalars. And so I would essentially have an A11 V1 plus an A12 V2 plus an A13 V3 plus, and this would go all the way down until I get to the end with M. I want to make sure I've got the right numbering system here. Excuse the notation. This would be here, 2, 1, 3, 1. Dyslexia kicking in a little bit. A, M1, and then VM. And so if I perform this combination, I would create W1. So if I want to create W2, this vector, I would do that using the scalars of A21 V1 plus A12, A22, A32 V3, all the way down until I get to AM2 VM. So notice how this is essentially coinciding with the second component. It's essentially the columns. And if we continue this process down all the way to WN, we would create an A1N V1 plus A2N V2 plus, this would go all the way down to the end to AMN VM. And when we're looking at this process, with all of these combinations, notice that I'm essentially taking W and I'm setting it equal to two matrices that are being multiplied together. And it's the matrix of V, which contains these vectors as my column, times the matrix that has these A entries as row and column entries. And so it ends up writing it like this. It's W is equal to VA. And you can see kind of the notation in the textbook there. And when we're looking at this combination, the argument is that if these two things are bases, then there shouldn't be any free parameters. The only solution set should be equal to 0. Remember, basis, everything is linearly independent, and they span whatever the space is. We have just the right number of vectors needed to form every possible combination. And when I'm looking at this matrix, if n is greater than m, then I want you to pay close attention to the matrix for A, because when I look at A, V has m vectors listed. A would then have to be an m by n matrix in terms of the multiplication. And when I'm looking at that in terms of A, because n is greater than m, this matrix is shorter than it is wide. In other words, I have less rows than I do columns. And in the previous videos, when we were talking about this in terms of independence, if that's the case, then not every column is going to have a pivot in it. There's too many columns. That means there are free variables. It means that this can't be a basis because it's essentially being formed by something that has more than just a 0 solution to AX is equal to 0. And this is why this can't be the case, because we're assuming that there's only one unique solution here if these are bases. So when I'm going through and I'm kind of solving this, that's our kind of contradiction point. And so we're saying, okay, well, n is greater than m. Well, if I change this and say, okay, well, m is greater than n, if I go the other way around, we just swap the matrices. I swap this combination. We're going to get something similar. That again, V is equal to WA, where A again is a short and wide matrix. If I was to solve this for WX is equal to 0, remember we're saying that if this is a basis, the only answer to this should be 0. But by setting something up, we're going to show that there's more possibility. 0 is not just the only answer to this. We can actually create anything because of this being short and wide. And so it stems again from this idea once we kind of create this factorization. So what that ultimately tells us is this kind of somewhat intuitive idea, but we now have a proof behind it, which is if you have two bases for a set, those bases have to contain the same number of vectors. And the book goes in and kind of highlights a little bit more in terms of the language of linear algebra, so I would encourage you to read and take a look at the bottom of page 120, because we want to be really careful in how we talk about these things. He says we never say the rank of a space or the dimension of a basis or the basis of a matrix. The terms don't have meaning. So dimension describes space, right? That's what we're looking at. A basis helps describe the combinations it takes to span a space. And when I want to talk about the dimension of that space, we count the number of vectors in the basis. That's the idea. Rank of a basis, rank of a column space, all of those kind of things. Rank of the matrix, like there's connections there, but we got to be really careful in terms of the terminology. And so he again kind of explains, it is the dimension of the column space that equals the rank of the matrix. And so making sure that we're being careful. And then outlines 4 key things. This is what the next lesson will again kind of highlight, specifically focusing on the dimension of these spaces, which is the row space has dimension R, then the null space would have dimension n minus R. The column space would also have dimension R. Column space and row space have the same dimension. But the null space of A transpose, so that's the null space of the row, looking at the rows, would have dimension M minus R. So if N is counting again the number of columns, M counting the number of rows, we can kind of see the connections between both of those. The null space essentially saying total number minus how many pivots you have. Because remember the pivots, the number of pivots, the number of vectors for my particular solution that we saw in 3, and putting it all together is equal to R. That's that number there. The null space would then have to be N minus that, and we saw that again with the matrix I and the matrix F. So this is the idea of dimension, kind of proving that for a space, in particular subspace. Again, if you have questions on this, please let me know. If there's a high demand for the worked examples, again, we will work some in class and work some with you if you have questions over it. But otherwise, keep a lookout for 3.5.